Hey everyone, and welcome to our next lesson in Unit 5. Today we're going to be learning about how to interpret excited and ground states of electrons in atoms. So by the end of today, you should be able to interpret those electron configurations and determine whether or not an atom is in an excited or a ground state. Now remember, this is a little bit of a review. The ground state is when electrons are occupying the lowest possible principal energy level. It's the most stable place for electrons to be, and this is the configuration that we find on the periodic table. Relatively straightforward here. Now the excited state is when one of those electrons absorbs enough energy to rise up to a higher principal energy level, gaining energy and jumping up to that less stable, so more unstable state. And this is going to be any configuration that's not listed on the periodic table. Now this is considered less stable because those negatively charged electrons are still attracted to that positively charged nucleus and are trying to move back down. And as we have electron transitions, it is not considered a stable state. Now, if you remember, kind of review from a couple lessons ago how light is produced using electrons in an atom. And we know that when those excited electrons fall from that excited state to the ground state, energy is being given off in the form of a photon. And the bigger that change, the bigger that drop, the higher energy in the drop, the higher energy of the photon. So larger drops, higher energy photons we find in the violet range, and lower energy ones we'll find in the red range. Depends on how much energy the photon has, depending on the drop and where it falls on the electromagnetic spectrum. But as these electrons transition from excited to ground state, they're giving off photons from the energy that they initially absorbed. So let's say, for example, we have an atom colliding with another atom, or some particle causes an electron to get excited. And we see one of these electrons kind of jump up. They jump up to the next energy level. So they gain that energy from a collision. Electrons get bounced and jump up, and the atom gets excited. Now, when that electron returns and comes back down, that's when we see our light photon being given off as that energy that was gained is released once again. So we know that atoms, when we're talking about an atom itself, we're talking about a neutral particle. So atoms are neutrally charged. So protons have to equal the number of electrons. So as long as we know the atomic number, we know that nitrogen has 7 protons, and therefore is going to have 7 electrons since it is an atom and atoms are neutral. So we can determine those particles back and forth as long as we know one, and we're referring to an atom. The electron configuration here is the ground state. This is the stable state for electrons in a magnesium atom. Now there can be many different combinations of electrons to come up with almost countless configurations depending on how many electrons we have. We can have more configurations the more electrons we have in different amounts of principal energy levels, but the total number of electrons is not going to change. That's going to remain the same. So the total is going to remain the same. They just might move and shift between different PELs. So as long as there's the same total number of electrons, and some of those are in higher energy levels than compared to their ground state, then the atom's considered to be in an excited state. So for nitrogen, its base configuration, its stable ground state configuration is 2-5. Now, any configuration that has a total of 7 electrons with some in higher energy levels is going to be considered an excited and more unstable state. Now, feel free to pause this and see if you can come up with some excited configurations for each of these, and then check your work. So for nitrogen, we have a total of 7. Let's say we had an electron here and the second jump up to the third. We might get a configuration of 2, 4, 1, which totals 7, and therefore that works. Another example could be something like 2, 3, 2. Again, still adding up to 7. In this case, we can see that 2 electrons jumped up from the second up into the third principal energy level. For magnesium, the ground state configuration is 282. So we could see something like maybe 2811. Again, still tallying the 12 that we need. We could see something like, let's say 1821, where we still have 12, which is the total we need to keep our neutral atom. But we had one that went from the first up to the fourth. So we can see with more PELs and more electrons, we can have a lot of transitions that can happen. For chlorine, base configuration of 287. This is the ground state, 7 valence electrons. So we could do something like, let's say 2816. We could do something like, let's say 2771. As long as they're adding up, let's see, we're going to need 17, then we're okay. And we have 17 in each of these. So we're maintaining our neutral atom. Now we can take a given principal energy level configuration and determine some information from it. We can determine what type of element we have. We can determine if the atom is in an excited or ground state configuration. For example, if we're given this configuration of 2883, we can first tally these up to get a total of 21 for the first example here. And then we can use that to try and figure out what element we actually have. So if we have 21 electrons, that means we should have 21 protons. So an element with atomic number 21 would be scandium. The electron configuration from the periodic table. And the configuration from the periodic table would be 2, 8, 9, 2, giving us a total of 21. These configurations do not match, so this would be an excited state. In this case, we can see that the next one here, we tally up this configuration to get the total number of electrons. We get 11. This would be element sodium. And the configuration from the periodic table is 281. These configurations do not match. Therefore, this has to be an excited state. For the next one, we tally these up. We get a total number of 14. This would be silicon. And the configuration from the table would be 284. So the totals match, but the configurations do not match. And for our last one here, the total number of electrons that we have. Let's see, we'd have 25, we'd have 27 here. This would be element cobalt. And the configuration for cobalt from the table is 2, 8, 15, 2. This does match, so this would be considered the ground state. Relatively short topic here, relatively straightforward. If you guys have any questions, make sure you come see me to get your questions answered. Hope everyone has a great day.